We have question number 17, which is the last question of our this module. Imagine you are planning an interstellar journey to Proxima Centauri, the nearest star to the Earth Sun, located 4.25 light year. Okay, that is interstellar journey. Interstellar journey is actually the way between two or distant places. 4.25 is the length of the or the light year for that journey, while one light year is equal to 9.461 crust and raised per 15 meter. For practical reason, let us assume maximum speed for space travel is 66,000 km per second. Your spacecraft has following specification. A spacecraft having the mass 1000 tons in kilogram, it has almost 1 lakh kilogram. And length is 20 meter and projected area is 24 square meter. The interstellar medium has a number density of about hydrogen atom per cubic centimeter. As it is traveling in the space, there is actually more amount of the hydrogen atom in the space. So they can produce a dragging effect for its motion. But we will see how much this effect will be due to hydrogen atom on the spacecraft. The mass of hydrogen atom is 1.67 crust 10 raised to minus 27 kilogram, and the number density of hydrogen atom is per cubic centimeter. Per cubic centimeter is its number density. And here are a few questions that are asked about which we need to answer. What is the total mass of hydrogen atom that your spacecraft will encounter during the trip? What is the total mass? First of all, we need to check the given data that is given to us. And yes, here we can write. This question is also a time-taking question. Okay, first of all, let us talk about the distance. Distance is 4.25 light year. That is given to us. Light year. And as 1 light year is equal to 9.461 crust into 15 meter, then let us convert it into meter. 4.25 multiplied by 9.461 crust and raised power 15 meter, which will results 4.02 cross 10 raised to power 16 meter. That is a distance from the point of you can say departure to the point of landing. Okay. Next thing that is given, ship speed. Speed of this spacecraft is represented by you here is 60,000 kilometer per second. You can convert it into meter per second just by multiplying by 10 raised power 3. Then it will become 6 cross 10 raised power 7 meter per second. That is the speed of the spacecraft. Okay, ship mass is, let us check its mass is 10 raised power 6 kg. Representing it by capital M is equal to 10 raised power 6 kg. Okay, next is projected area. Area of the ship that is given is 24 meters square. And hydrogen atom density that is given us, N is equal to 1 atom per cm cube. But our SI unit are meter cube, not cm cube. We need to convert it from cm cube to the meter cube. If you want to move from centimeter to the meter, you need to divide by 10 to the power 2. If you want to move from centimeter cube to meter cube, you need to divide it by 10 to the power 6. As it is already in the division, then it will become 10 to the power 6 atom per meter cube. That is actually number of atoms density, and remaining time is less than 1 minute. We need to recreate the meeting. Okay, mass per hydrogen atom, and mass of each hydrogen atom that is given to us is equal to 1.67 cross 10 raised power minus 27 kg. Okay, that is the mass. So that is completed, and let us check the first requirement. What is the total mass of hydrogen that your spacecraft will encounter during the trip? What does it mean? It's mean from the point of departure to the point of landing, between that it is encountering the hydrogen atom. So question is that how much hydrogen atom will be encountered, or the total, how much will be the mass of the hydrogen atom that are encountered? Let me understand you like this. Okay, let us suppose that is the way in which a spacecraft is moving. Just for example, it is a path in which spacecraft is moving. I don't have very good drawing. You know, just you need to understand. This is spacecraft that is moving. Okay, it is moving in this direction. We need to now understand the hydrogen atom that are lying in its path on which it will need to encounter. And the thing that we know is actually, we know the distance from the point of departure to the point of landing. We know, we have calculated here, you can see that is the distance, total distance. And what we have now, we also have the area of this aircraft. If we will multiply this area with this length, let's suppose this is the area of aircraft and this is the length along which it is moving, then we can calculate the volume of this whole path. That whole path volume will represent the number of atoms or the mass of the atoms that are encountered. So let us do it. So let us first of all calculate the volume that is swept, in this case volume swept by the spacecraft is equal to area of the spacecraft multiplied by the total distance d is equal to A, that is 24, multiplied by D, that is 4.02, multiplied by 10 raised power 16. That will results 9.65 multiplied by 10 raised power 17 meter cube. It is the volume of hydrogen atoms, or the path that is following by the spacecraft. It is not the mass of the hydrogen atoms. So now we know the volume. If and also we know the number of hydrogen atoms per meter cube. Here you can see number of hydrogen atoms per meter cube we also know. If you know the volume in which hydrogen atom are existing, and also you know the number of hydrogen atom per unit mass, then you need to multiply it to calculate the number of atoms. So number of atoms is equal to n multiplied by volume V that we have calculated. N is 10 to the power 6 multiplied by volume is 9.65 cross 10 to the power 17. That will results 9.65 cross 10 to the power 23. That are actually number of atoms in this complete way about which we are talking, the way which is mirrored in the light year, this way. In this complete way, the number of atoms are 9.65 cross 10 to the power 23. That are the hydrogen atom total. Now, if these are the total number of hydrogen atom, if you know the mass of a single atom, then multiply that single atom mass with these total number of atoms, then you will be able to calculate the total mass of hydrogen atom. So let us multiply 1.67 is the mass of single atom cross 10 to the power 27 minus multiplied by 9.65 cross 10 raised power 23, which will results 1.61 multiplied by 10 raised power minus 3 kg. Around about 1 gram is the total mass of hydrogen atom that are lying between these two locations. That is a mass of hydrogen atom. Okay, next case is speed of hydrogen atom after collision you need to find. Speed of hydrogen atom that you need to find. Okay, if I want to compare the mass, here we are talking about the two masses. One is the mass of spacecraft, other is the mass of hydrogen atom that are colliding with the spacecraft. If m is the mass of spacecraft and small m is the mass of hydrogen atom, then mass of spacecraft is very greater than the mass of hydrogen atom. So that negligibly you can say as compared to the mass of spacecraft, it is equal to 0. Okay.
Mhm.
So speed of hydrogen atom after collision will twice the speed of spacecraft. That is a supposition that speed of hydrogen atom will be twice after collision with the spacecraft. For example, in this diagram, if this spacecraft is colliding with this atom, then its speed will be double of the speed of this spacecraft. For example, if spacecraft is having 60,000 kilometer per second speed, then speed of this hydrogen atom will become 120,000 or 1,20,000 kilometer per second speed. It will be doubled. And let me prove how it will be doubled. Again, we will use the results as hydrogen atom is a second mass and uh, spacecraft is first mass, then V2 prime relation is equal to 2m1. These relations are with us, they will never leave us. m1 plus m2 into v1 plus m2 minus m1 over m1 plus m2 into v2. So V1 is the velocity of the spacecraft, V2 is the velocity of the hydrogen atom, M1 is the mass of the spacecraft, and M2 is the mass of hydrogen atom. So let us replace these values in this equation. And V2 is the velocity of the hydrogen atom, which was initially at rest before the collision with the hydrogen spacecraft. Then this term will be equal to 0. Then the remaining term is only this term, which you need to write to capital M, as we are ignoring the small mass m plus capital M into V. So you can ignore it. M can cancel them is equal to 2V. is the final velocity of the hydrogen atom, that is a second object in this case. Hence, it is proved that when hydrogen atom will collide with the spacecraft, its velocity will be double of the velocity of the spacecraft, that is 2v. Is it clear?
Yes.
Now let us check how much it will be the doubled. We know the velocity of the spacecraft is 60,000 or 6 cross 10 raised power 7 meter per second. As it is need to be doubled, then it will become 1.2 cross 10 raised power 8 meter per second. That is the velocity of the hydrogen atom after collision with the spacecraft. So that was the answer of our second question. Let us move towards the third question. I need space. Okay, I need space, but if I will delete, then from where I will find the values? Okay, question number 3. What is the total impulse delivered to the spacecraft by the interstellar medium? How much this medium is providing the impulse to the spacecraft, that we have to find in our next case. Impulse is actually the product of mass and velocity, or the change in momentum. And in case of the initial impulse, initial momentum will be zero for the hydrogen atom, because initially they were in rest initially. And after interaction with the spacecraft, they gain the velocity, so they will have some final momentum. So total for the impulse, I is equal to change in momentum is equal to the product of the mass and change in velocity. Product of the mass is actually the total mass of hydrogen atoms, that is 1.61. We have calculated the total mass of hydrogen atom in our first question. Minus 3 kg multiplied by the velocity. While velocity we also have calculated 6 cross 10 raised power 7 meter per second for the hydrogen atom. Okay, then its velocity, its impulse will become 966,965 kilogram meter per second. That is impulse. So our question was that what is the total impulse delivered to the spacecraft by the interstellar medium? This interstellar medium is providing the impulse to the spacecraft, that is 96695 kilogram per meter per second. And this medium is consisting on the hydrogen atom, whose mass we have measured, and we have utilized that mass in this question. Okay, question number 4. Is this impulse significant when compared to the momentum of the spacecraft? We have measured the impulse. Is it significant? For that purpose, we need to measure the ratio of the impulse to the momentum of the spacecraft is equal to 96695 divided by the product of mass and velocity of the spacecraft, and mass which is yes, mv, mass of the spacecraft multiplied by the velocity of the spacecraft. So let us replace the values in it. 96695 divided by mass is 10 raised power 6 multiplied by the velocity is 6 cross 10 raised power 7. You can observe the denominator is so much greater as compared to our numerator. 10 raised power almost 8 time, 9 time it will be greater. For example, I want to write the numerator and denominator in the scientific notation. Then the upper value will result 9.6 cross 10 raised power 4 divided by 6 cross 10 raised power 13. That is a difference round about 9, 10 to the power 9 time difference. So the resultant value is actually 1.61 cross 10 to the power 9 minus 9. It is showing that as compared to the momentum of the aircraft, the impulse is some billionth part of the momentum of the aircraft. So it is not disturbing the motion of the aircraft, spacecraft, because impulse as compared to the momentum of the spacecraft having the very low value, 10 to its power almost 9 to 10 time is it has the low value, so it will not affect on the motion of spacecraft. Is it clear?
Yeah, it's clear.
Question was that significant when compared to the momentum of the, so it is not significant. It is very small quantity, will not affect on the motion of the spacecraft.
Hmm.
Last question. What is the effective drag force exerted by interstellar medium during the journey? We need to calculate the effective drag force. Drag force is actually the formula for the drag force that we have studied is Fd is equal to 1 by 2 rho A CD V square. Here they are not given have given us a row area CD of the medium. So we will use a different way to calculate the drag force. We will use the relation of the impulse for that purpose. Impulse is actually the product of force and time interval is equal to change in momentum. So as you need F is equal to del P over T, while time is not given, but we know time is actually the ratio of distance and velocity. Then our equation will become del P multiplied by V divided by S. S is in light year, we have calculated already. So del P also we have calculated, that is 96695 that is impulse multiplied by the velocity that we have calculated 6 cross 10 to the power 7, it is actually given to us, divided by s is the distance in the light year 4.02 multiplied by 10 raised power 16, which is providing the result that is 144 cross 10 raised power minus 6 Newton, or you can say 144 micronewton, which is drag force value. And again, it is an evidence that drag force is so much weak that it is nothing in front of the momentum of the spacecraft, so you can ignore it. Okay.
Yep.
Okay, now finally you have a look on the last question. Where is that? Okay, here is that. Given distance in the light year, converting light year to the meter has become 4.02 cross 10 to the power 16. Ship speed is 6,000 km per second. 6 cross 10 to the power 7, and ship mass is 10 to the power 6. Area is 24 meter square. Hydrogen density is given 1 atom per cm cube, and we need to convert it from cm cube to the meter cube. So 10 to the power 6 atom per meter cube, and mass per hydrogen atom is 1.67 cross 10 to the power minus 27 kg. We have to calculate the total mass of the hydrogen encountered. So it will be equal to, first of all, we need to calculate the volume of the way in which these atoms are encountered. So is equal to A cross distance. Distance in the light year is this given, while area of the aircraft is 24. So it is a volume. Now number of atoms you need to find. So atoms density per single atom per meter cube is 10 to the power 6 multiplied by the volume, and these are total number of atom. If you know the total number of atom and you know the mass of the single atom, you need to multiply them to calculate the mass. That is 1.61 plus 10 to the power minus 3 kilogram. Second part, speed of the hydrogen atom. We know mass of aircraft is very greater than the mass of the hydrogen atom. So we have the formula as we are here to calculate the speed of the hydrogen atom. That is the second mass. So final velocity of the second mass is equal to m1 over m1 plus m2 v1 plus m2 minus m1 over m1 plus m2. As the second body was initially at rest, so equal to 0, and m1 is ignorable, m2, which is a smaller mass, can be ignored. Then 2m over m, you can cancel m by m, and it is 2v1, while v is 60,000 kilometer per second. So put here, that is 120,000 kilometer per second. That is actually the velocity of the hydrogen atom. That is twice after collision. Next is the impulse. Impulse is the time rate product of mass and velocity. So total mass of the hydrogen atom that we have calculated in first part multiplied by relative speed. So relative speed is 6 cross 10 to the power 7 and 1.6 cross 10 to the power minus 3. Here you need to use the relative speed instead of the speed gained by the hydrogen atom. So relative speed will provide you the result 9.69695 kilogram meter per second. Next is effective drag force. It is actually the fifth part. Mistakenly, I have done fifth part first and fourth at the end. So you can check here, drag force is equal to del P over time. Del P change in momentum over time. Time is d over v. So putting the value, simplifying, v is the velocity, that is 6 plus 10 to the raised power 7. Del P is the momentum that we have calculated here in our previous part. Over d is the path in the light year, 4.02 cross 10 to the power 16 in the meter actually. So it is drag force 144 micronewton. That is so much small and we need to ignore it. So drag force exerted by the interstellar medium is extremely small as compared to the momentum of the spacecraft. Therefore, it can be neglected for the practical purposes. Now compare the significance, del P or P ship. So P ship is the momentum of the ship or the spacecraft, while del P is the impulse provided by the interstellar medium that is actually consisting on the hydrogen atom. Simplifying, finally you can compare the powers, that is almost for the billionth of the time. This means total momentum transfer from the interstellar medium to the spaceship is about 1.6 billionth of the ship's initial momentum. Ship's initial momentum, billionth part of that. So again, it is ignorable. So there is the impulse produced by the interstellar medium have no effect. It is not significant. You can ignore it. So finally, we have completed. Okay. So do
Very
you have
nice.
any question?
No, I don't have any questions. I think it was very clear.